This lecture, we're going to go over a little more depth the concept of non-inertial reference frames. And these can be a little bit tricky, but as we go through, we're going to go through a couple interesting examples and some of the things that they cause. So to start with, let's go over our definitions from last lecture. An inertial frame of reference means there's no acceleration. Everything's moving along with a constant inertia. On the other hand, non-inertial means there is acceleration. It means that inertia is not being conserved. And I know this can be a little bit confusing. It's not always obvious which is which, and it's just one of those things you do have to try to remember. There's no easy mnemonic to make it obvious which one's which, but you try to remember that inertial is the one that's easy to deal with, and non-inertial has acceleration, making it a little trickier. So the question is, when would you use non-inertial frames of reference? And a lot of times with gravity, because gravity behaves as acceleration. It's a constant acceleration based on how much mass is gathered. You'd use that, but that's a fairly complicated example. You probably wouldn't use that until you did relativity or some other kind of advanced physics. But the example we're going to use is something rotating. If you have a rotating object, say a merry-go-round, you'll notice that everything seems to slide towards the outside. Now, why is that? It's not because there's a force pushing up. It's not the wind. It's not the merry-go-round somehow pushing on the object. And that's instead because things need to be pulled in towards the center to stay inside the frame of reference. Because believe it or not, a rotating merry-go-round is actually accelerating. Because when you look at it, let's pick a point on the edge here. The point has some velocity v, and it's in whatever direction the edge is spinning, which is currently in the right-hand direction. Now, as this merry-go-round spins, on the right-hand side, it's going to point straight down. On the bottom, it's going to point over. And by similar logic, on the left-hand side, it's going to go straight up. So because of this, we can see that something's changing this velocity. Something's pulling it in a circle. And what you can notice is the direction the velocity is pointing rotates. It's pulled in, and all this pulling, this rotating of the direction of velocity, always pulls in towards the center. So we can say that the velocity is accelerating in towards the center. And this makes a lot of sense when you think about it. If you imagine the Earth sitting in space, and then the moon's orbiting it. The moon's traveling in a circle, that's its velocity, but its acceleration is inward because of gravity. And we get the same kind of thing in our rotational frame of reference. The objects are moving in a circle, but they're actually being accelerated inwards at all times. Now, why is this interesting? Well, this is interesting because this produces some really cool effects. On the example of the merry-go-round, if you sat on one side of a spinning merry-go-round and try to roll a toy ball across the merry-go-round, instead of going straight across as you'd expect, you'd find that it would curve off to one side or the other, depending on which direction it's spinning. And this is called the Coriolis Effect. And it's based on the fact that the spin of objects causes them to seem to accelerate outwards. And the reason this is because our frame of reference is non-inertial. There is acceleration. Now, when can you see the Coriolis Effect? Interestingly enough, we actually live on a non-inertial frame of reference. The Earth, as it spins, is not inertial. That all parts of the Earth are being slightly accelerated inward to counteract the spinning motion that the Earth undergoes. And on the small scale, you can't actually notice this. But on the large scale, it actually becomes really important and really interesting. For instance, in World War II, when they had really long-range artillery in force, they would actually have to adjust for the spin of the Earth as the Earth spun under the shells that were being fired. And similarly, really large storms, like hurricanes, spin in a specific direction in the northern and southern hemisphere because the Coriolis effect exerts different forces on the east and west tips of the hurricane. Now, a lot of stuff gets attributed to the Coriolis effect. People claim this because of the Coriolis effect, but it really isn't. For instance, one of the common ones is water going down a sink. People say that the direction the whirlpool going down a sink forms is a result of the Coriolis effect. And that's really not the case. And the reason is the distance between the edges of the whirlpool is maybe a few inches, up to half a foot if it's a really big whirlpool. And that's just not enough distance for the Coriolis effect to take place. It depends on a really large separation of distances. So as a result, little whirlpools, the ones going down your sink, and even tornadoes and such, are not affected by the Coriolis effect. But big things, like a hurricane or like the flight of artillery shells as they go 20 miles, can actually be affected by the Coriolis effect. And this all traces back to the fact that since the Earth is a non-inertial reference frame, that as this ball on the merry-go-round, our example, rolls, the merry-go-round is turning under it, and the ball isn't turning. So the ball keeps going in the direction it was launched, horizontally as well as straight forward, while the merry-go-round turns in a circle, creating the impression that the ball is arcing out. And it's not that some force is acting on the ball. This is one of those cases where we can't describe it in terms of forces. And here, the actual issue is we picked a bad frame of reference. We picked a frame of reference that's non-inertial. And you won't have to do much work with this throughout the course. So you might do a little bit in the case of rotating objects. But for the most part, it's just important to know that when you pick a frame of reference, it's always important to make sure that it's actually non-inertial. It's traveling at a constant velocity in a straight line.